Yeah, hello to our statistics course, and we will start with short introduction and a short review. What is statistics about? And for this, I want you to remember, what is a random variable? By assigning the topics for the term paper, you saw that we have this general problem. What is a random variable? What is a true random variable? And yeah, definition is just that a random variable x is some specific mapping of anything, more or less, into the room of the real numbers. So we can choose the color of your eyes and mapping this then, that blue is 1, red is 2, and so on and so on. And then we say that the probability of this mapping, that our random variable, let's say color of your eyes, equals one element, what it could be, say green, and then we know the probability. And the probability P is of a random variable is then the specific probability that this random variable is equal some specific element. And if we all have this, then we call this afterwards a distribution. So in this we can say that then every random experiment we can express as a random variable. And there, if you look then also in the books, there we distinguish between the random variable, which is written down in capital letters. So capital X is the random variable, and small x is then the sample, is then the element of the sample space. And one prominent example for random experiments is just rolling dice. So in general, our random variable is the number of the dice which we roll and the elements. What can this random variable afterwards be is 1, 2, 3, 4, 5, 6. So capital X equals then, after we have thrown our dice, for example, 3. And this we call then the realization of a random variable. So in my example, I said x equals 3, or for example, the random variable capital X realizes the value x equals 5. So, and since before, as we said, onto the real numbers, and the probability is known if we have fair dice, well, then it's not that hard for you to say me what is the probability rolling dice that the realization the outcome after throwing is smaller than 5. What would it be? What do we assume when we have a fair dice? Possible outcomes 1, 2, 3, 4, 5, 6. Yeah. That for every single number we have a uniform distribution, and then it is 1 over 6 for every single number we have the same probability, and therefore P of capital X equals 1, for example, is 1 over 6, and so on. And what is then the probability that our outcome is smaller than 5? Yep. Yes, because then we have just to sum up the probability of x equals 1 plus probability x equals 2, and so on. So we obtain that this is then p of x equals 1 plus p of x equals 2 plus p of x equals 3 plus p of x equals 4 is 1 over 6 plus 1 over 6 plus 1 over 6 plus 1 over 6 is 4 over 6. Maybe in your introductory courses you have also flipped coins or drawing cards. I don't know, something like this maybe. Okay, but then we have to distinguish what we have when we are rolling dice is that we have a finite or countable set of realizations. So for example, if the possible realizations are the natural numbers, then there are, of course, infinite amount of natural numbers we have, but they are countable. 1, 2, 3, 4, 5, 6, 7, and so on. And this we call then a discrete random variable. But we quite often look also at so-called continuous random variables. And these continuous random variables then have a realization of an interval and now of the real numbers. And hopefully you have talked about this in school, that you cannot count the real numbers. So there is no direct mapping between the real numbers and the natural numbers. But this is more a philosophical aspect. But since we cannot count the real numbers, this, on the other hand, means that if we have a continuous random variable with the probability, so to speak, that we have a specific outcome is then 0. Because if we then want to sum up all specific events, this is not possible because it's not countable. And this is yeah, the main difference between discrete and continuous variables. And in this table, I showed you again, when you have a discrete random variable, then it's somehow easier or more intuitive what you can do, because then you can really say if X has a specific realization, then we know the probability. And if we go to a continuous random variable, then we have no probability mass function, but we have to go to the probability density function, because P of X would be 0. So a single event has probability mass 0 within a continuous random variable. The probability mass of a single event is 0. Well, and then if you remember my example, what is the probability rolling dice that the number is smaller than 5? We calculated this to probability of 1, probability of 2, probability of 3, and so on. And what we have done there is just calculating the so-called cumulative distribution function. And for a discrete variable, this means we just sum all these probabilities up. Rolling dice, all the probabilities are the same, but we can think of other random experiments where these probabilities pi are different. Well, and if we go then to the continuous random variable, then we just exchange the probability mass function with the density function and the discrete summation with the so-called continuous summation, and this is just integrating. Well, and then for describing a distribution, we are interested in these specific numbers with which we standardly describe distributions. And this is quite often to calculate the expected value. And what is the expected value? This we define in the discrete way by the sum of the realization times the probability of the realization. And then quite often for an estimator of this expected value, we quite often calculate the mean of our distribution. But keep in mind, this is not the same. Calculating the arithmetic mean means not that this is always the expected value. This is our estimation. that on average in a distribution we calculate the arithmetic mean. But we see here, if all probabilities like rolling a dice would be the same, then this expected value becomes directly the arithmetic mean. Okay, and then again, like when we go from the cumulative distribution function, when we looked at this, we also just interchange the summation sign with the integral. And then the second moment, we mostly say, well, not every outcome is, of course, our average, our expected value. We have some fluctuation around our expected value, and this fluctuation we call the variance. And the variance then is defined as the sum over the squared distances between our realization and the expected value. I don't know, have you talked about the issue why we are taking the square and not up to 3 or absolute value or something like this in introductory courses? I have to write a bit larger. Or so. But expectation value, variance, and so this you know, or this you have already heard. Okay, and with these things, we quite often have to deal, and therefore it is good to know how to calculate with the variance and the expected value. Because quite often we just manipulate our data. So we take a random sample and then we multiply our numbers, our outcomes, or we go further and add some numbers. And then we want to know, how does this change the expected value and how does this change the variance? Well, and of course, if we have a constant, then this means that the expected value is the constant itself. And not very surprisingly, the variance of a constant is of course 0 because there is no fluctuation. And now manipulating our random variables. So now we want to multiply our random variable with a constant a. And this means that this constant we can just put out the expectation operator. How do we see this? Well, if we look here at the definition, and if we would write just in front of our realization here some constant, then the calculation rules of this summation operator means just, okay, this can be put out in the to the summation. For example, if we sum up sum of 1 plus 4 plus 6 and we multiply every number with 2, so then 2 times 1 plus 2 times, what did I said, 4 plus 2 times 6, then of course we can also calculate 2 times brackets open 1 plus 4 plus 6 closing brackets. This is not really complicated, and the same rules we have also with the integration sign. A constant we can take out of the integration process. Okay, but if we take the variance, there we have to be careful, because now if we take out our constant, this means that we have to square this constant. Well, also this we see directly here. If we put in here an a before our realization, then we also have to keep in mind this changes, of course, also our expected value. What have we learned from the expected value? That an a here means we can take it out. So writing here an a means we have to write also here an a, and then you can take both of these a's outside the bracket, but you have here the exponent 2. So if you want to take this in front of your summation sign, then it is of course an a squared. And the same would be the case here. Yeah, and if we take these calculation rules together, then we come to the linear transformation for the expectation value, taking this rule and this rule together means then that if we linearly shift our random variable, multiplying with some number and adding a number, that the expectation value then shifts in the same way. So this means the expectation operator is a linear operator. But taking this together, this rule and this rule for the variance, then of course a shift of a constant number b, there we know the variance of a constant is just 0, that this vanishes. Well, intuitively, I think it's also clear. If we have any random experiment and the realization is, let's say, around 2, and then we add 10 to every realization, then our distribution just moves 10 points to the right. This should not change the fluctuation. But if we multiply our random variable with a constant, then we have to take out the square of this constant. So this means variance is no linear operator. Okay, and now, or then next week, what we then want to start is that we are looking after having generally defined, or hopefully you remember what is a random variable, what is an expectation value. Now we go to the descriptive statistics, and after having a random sample, then we start to describe our distribution. We somehow want to get out information of our distribution. And for this, we calculate different numbers. And at first, of course, there is not only the arithmetic mean as an estimator for the expected value, we have different means or median parameters. And one is the median, the arithmetic mean, geometric mean, harmonic mean. I think the arithmetic mean, of course, everybody knows it. I think the most of you have also entered my macroeconomics course there when we were averaging growth rates or inflation rates. Then I talked a lot about when we have in economics to apply the geometric mean, and there's also the so-called harmonic mean. And then we have possible parameters in order to describe the dispersion around our chosen mean. And for this is, of course, the easiest one, the range. So we take that just the distance between the highest and the lowest value. We could calculate the mean absolute deviation, the sample variance, biased and unbiased. Have you heard about this in your introductory courses? Because here we divide the squared distance of our numbers minus the average by 1 over n, and here we divide by 1 over n minus 1. Do you remember this? Well, let's just step in this one, that we define it once in this way, and in another case we define it this way. I don't know, have you talked about why we choose in general this for the variance or not? Well, maybe we do this in an exercise. Okay, then taking more or less the square root of the variance, this we call then the standard deviation. And then I will introduce in this course also two more parameters called the skewness and called the kurtosis. If we take this, this is more or less something like xi minus mu squared. And this would be then something like xi minus mu to the third and xi minus mu to the fourth. And this we then call, because of these exponents here, third moment, fourth moment. We can, of course, go further, calculating fifth moment, sixth moment, and I think it was the eighth topic of the of the term papers where you should deal with this method of moments describing a distribution. Okay, and then I think next week we will create some random sample and just calculate all these numbers that you remember, what you hopefully have done in your introductory course. Okay, then thank you very much for today.